In section 7.6, I want you to be able to use the number e to write and graph exponential functions representing real-world situations, and also to solve equations and problems involving e or natural logarithms. So let's talk about what e is. So in section 7.6, you'll be working with another logarithmic base that's programmed in your calculator. We already talked about base 10 that's programmed in your calculator. This base is e, and it is not a variable. It is an irrational number, like pi. When written as a decimal, it does not terminate or have a repeating pattern. So its value is 2.718, and then it goes to 281828, and you think it might repeat there, but then the next four digits are 4590. So there's no repeating pattern, and you can calculate as many decimal places of e as you want, and the pattern will never repeat or terminate. So the way that you calculate e is you take 1, and then you add 1 over 1 plus 1 over 1 plus 2, and then you keep adding 1 to the sum in the denominator. I shouldn't say 1, you keep adding the next integer. So here we added a 3, here we added 4, so this one would be 1 over, and the numerator is always 1, and the denominator always goes 1 plus 2 plus 3 plus 4 plus 5. So the next one would be 1 over 1 plus 2 plus 3 plus 4 plus 5 plus 6. And this is used a lot in the banking industry, and we'll have an example of that in just a couple of minutes. So exponential functions with the base of e is like other graphs of exponential functions. So this is f of x equals e to the x, and you can see it over here on the graph. It's exponential growth. It spikes at the right. The domain is all real numbers, because this is going to keep on going this way, and it's going to keep on going, so it's going to cover the x-axis. But the range, the smallest value, it's not going to cross that y-axis, so it's going to be, the values for y are going to be the set of all numbers y such that y is greater. We don't say equal to 0, because that's not defined there, so it's just going to be y is greater than 0. Okay, remember, e is not a variable. That's very important for you to understand. It has a value. All right, now if we look on the left-hand side here, a natural logarithm with a base of e is abbreviated as ln. Instead of writing log base e, you just say natural log. They have the same properties as other logarithms. So the natural logarithmic function is f of x equals the natural log of x. So it's understood that this has a base of e. So log without a base is base 10. ln without a base is base e, that 2.71828. So when you write ln, the base of e is assumed. So again, log base 10 of x, there's no base here, but there actually is. Base 10 is assumed. And there are only two bases you do not need to write, and that's base 10 when it's log, and base e when it's ln. Okay, so since the natural logarithmic function is the inverse function of the exponential function of e, so when it has a base of e, so that means the domain and the range, since these are inverses, the domain and the range are going to flip-flop. So here, the domain of the logarithmic function, which you can see over here to the right, this is f of x equals the natural log of x. You can see the logarithmic function is right here. The exponential function is here, and you can see that they're inverses of each other. There's your line, y equals x. So the domain and the range flip-flop from the exponential function to the natural logarithmic function. Okay, so when you're simplifying expressions with e or ln, the natural log, if you have, and I'm going to show this out longhand first, remember natural log, ln, the base is e, so I wrote it out like this, just so you could see that. We can use move the power out in front of the natural log, so it looks like this. And if you think of the natural log of E, which was the natural log base E of E, you say, what power do I raise E to get E? So anytime, which would be 1, anytime you see the natural log next to E, this just turns into the number 1. So this natural logarithmic expression is just going to be your exponent, 0.15t. Now the second one, we had an inverse property of logarithms similar to this, where if your base and the base that is in the exponent are the same, then the answer is just what follows the base. The problem is here we have a 3 in the way, so we need the natural log to be right next to E. So we can move the exponent 3 and put the exponent on here, so it's going to look like the e to the natural log base E of x plus 1 cubed. Okay, now, inverse properties say that if the E base, if you have a base of E, and then you have a base on the natural log here that is E, if these two are identical, then the answer is just what follows the base in the exponent. So our answer here is just going to be x plus 1 cubed. Okay, the third example we have is we have two natural logarithms added together. All right, now, when you have the natural log base E of E, again, that's just going to look like this. So you ask yourself, what power do you raise E to get E? And that would be 1. So we replace this natural log with the exponent 1. So what that means is if we are bringing this out in front, we just have 2x times the natural log of E, and the natural log of E, of natural log base E of E, is just going to change to 1. So this would just be 2x, and if we brought the x out in front here and we change this to a 1, that would be x. So we have 2x plus x, which is going to equal 3x. So whenever you have the natural log base E of E, the answer is just the exponent, and then you can just add those two together if it's an addition problem. Okay, I mentioned that E is used a lot in finance, so we're going to use E to calculate interest that's compounded continuously. Now this is different than what we used before when we had a percent increase or decrease. That's when you use this particular formula. But if you see that the interest is compounded continually, in other words, you're getting interest on your interest, then you use this formula. I call it the APERT formula. And it's A equals PE to the RT. So let's identify what each variable represents. A is the ending amount, so the same as what it was here. P is your starting amount or your principal, the amount that you're investing. E is a number, so it's 2.71828, so on. And R is your rate, and you need to write that as a decimal. And T is still time. So your rate and time are still the same as what they were here. Okay, so we want to know what the total amount for an investment of $500, so that's going to be your starting amount, your principal, invested at 5.25%, that's your rate, and remember we need to move the decimal 2 places, so it's going to be 0.0525 as a decimal, and we want to invest it for 40 years, so that's going to be your time equals 40 years. So you just go to this formula, and you just substitute all the values in. Again, 500 was your starting amount, so that goes in where your principal is. E is your number. And then you just want to be real careful when you multiply values in the exponent. You need to make sure that when you put E into your calculator, you have parentheses on both sides of what you want to be in the exponent. Otherwise, you're not going to get the correct answer. So your answer should be $4,083.08. So go ahead and enter that in your calculator and make sure that this is the answer that you get to make sure that you're entering it correctly. All right, the last thing that we need to do is has to do with half-life, and you'll probably do this in chemistry if you haven't done it already. Half-life is the time it takes for a substance to break down or convert to another substance during the decay process. And natural decay is modeled by this equation. And if you'll notice, I wrote down the APERT formula down here. It's very similar because you have a starting amount, which is here. You have an ending amount. You have E, and it's raised to the rate. This would be your RT. Now, K is the decay constant. It's the rate it's decaying, but it's negative because of its decay. It's getting smaller. It's not growing. Okay, here's our example. We have a plutonium-239. Now, this is just the type of plutonium, so that number doesn't matter for us. But it has a half-life of 24,110 years, and we want to know how long it's going to take for a 1 gram sample to decay to 0.1 or 0.1. This is a two-step process. The first thing that you have to do is you need to use this equation to find the rate of decay. Once you have the rate of decay, then you can just plug everything back in. So one thing about half-life is whatever you start with when you're dealing with half-life, your starting amount, and you look at your starting and your ending amount is going to be half of what your starting amount is. So half-life means that if you start with 1, you're going to end with 1/2. So you can basically plug anything in to this side of the equation that you want. You could start with 1,000 here, and you would put 5,000 here. Or you could start with 2 here, and you would put 1 here. So whatever this is, whatever number you're using here, you're going to divide it by 2 to get the number on this side. So your textbook uses 1 and 1/2, so that's what we'll be using here in this example, just to stay consistent with that. So when I set this up, this would be my starting amount. I have a whole unit, and after the half-life, it's going to end up at being half of its original weight. Okay, now we're looking for K, so we're going to put negative K, and then we are told that has a this should say half-life, so change that to life, has a half-life of 24,110 years. So that's going to go in here. We want to know how long it's going to take to decay. Okay, so first we have to find K. And we can use natural logs to do this. Since we're dealing with a E, we'll use natural logs. So if I add a natural log to both sides, I can use the properties of logs that say I can move my exponent out in front. So what I'm going to do is I'm going to add a natural log because I'm using base E. If I had been using a base of 10, then I would use log. So I add a natural log to both sides, which now allows me to bring this out in front. And now I have negative K times 24,110 natural log of E. Now remember, anytime you have the natural log base E of E, that changes to the number 1. So now, over here, we're going to have natural log of 1/2 equals negative 24,110 K. Okay, so I'm just going to take this value and divide both sides by that. And that leaves me with K, and this is going to be, we'll make this like approximately, because we're rounding off. And the more places you take K out, the more accurate you're going to be on your time that it's taking your substance to decay. So this is going to be negative point, I have 4 zeros, 287,493. So I took it out that many places. And this is my value of K that I'm going to need for the second part of the problem. Okay, so I use this value here. I'm not going to use that again. I want to know if I start out with 1 gram, that's my starting amount, how long will it take to decay to this? This is my ending amount. So I'll substitute those values in here. So starting amount goes here, ending amount goes here. So that means I have 0.1 equals 1 times e to the negative k. This is what I found for k, t. All right, now we're going to do the same thing as we did over here. We need to take the exponent out in front. So we're going to add a natural log. Now you can't just move the exponents unless you have logarithms. So I divided both sides here by 1, which is just going to give us 0.1 because you need to get the e by itself. So now we have 0.1 equals e to the negative, here's our k, times t. All right, now I'm going to add a natural log because we have e. Again, if it was base 10, we would add log. Natural log to both sides, and then I can move this value out in front. And when we have these two next to each other, remember that equals 1, so we can just kind of cross that off. And now I have negative kt equals the natural log of 0.1. So I'm going to divide by this value on both sides. And when I do, I'll find out how long it's going to take that sample of 1 gram to decay to 0.1. And that should be, we'll put a G on that too, the unit should be the same. Okay, so the time that it's going to take is going to be over 80,000 years. Okay, there are a few questions for you to try.